Good day and welcome to FlowNEX's sCO2 webinar. My name is Vali Lagranci and I have been an avid FlowNEX user for the past few years. In this webinar, we will look at the supercritical carbon dioxide cycle, also known as the sCO2 cycle, and how FlowNEX can be used in the design process and testing phase of the cycle. Furthermore, I would just like to indicate that the webinar will focus on using FlowNEX as a tool to model sCO2 cycles. We will focus on basic functionalities such as parametric studies and component modeling, and more advanced functionalities such as transients and control modeling. Various FlowNEX tips and tricks will also be shown for existing FlowNEX users that have joined us today, so we hope you find the webinar extremely useful, and please feel free to ask any questions in the tab on your right, where the FlowNEX team is standing by to answer any of your questions. Before we begin about the details regarding sCO2 modeling, I'd like to give you a brief overview of the FlowNEX software. FlowNEX applies a fundamental approach to thermal fluid network simulation using 1D flow and 2D heat transfer modular building blocks. FlowNEX contains components that simulate heat transfer and pressure drop correlations, and the user is also able to define their own correlation through FlowNEX's user-friendly scripting. FlowNEX contains a vast library of fluid properties obtained from RefProp and industry-standard software coupling, which is not limited but includes ANSYS, Mechanical, MATLAB Simulink, OPC Server, Excel, etc. FlowNEX is also designed within an NQA1 and ISO 9001 environment to ensure the best standards of quality compliance, nuclear verification, and validation. FlowNEX can be applied in power cycles and auxiliaries such as cooling water circuits and condensers, turbine and supporting systems, boiler and boiler systems, nuclear reactors, and in turbo machinery design, combustion chamber design, secondary flow analysis, cooling flow analysis, cycle analysis, and design. Before we jump into the main section of the webinar, I would like to remind the viewer to please feel free to ask any questions in the tab on your right, where the FlowNEX team is standing by to answer any questions. Here we have an sCO2 recompression cycle, where we have the main turbine, we have the compressor, the heating source, cooling, and recuperators. To date, the recompression cycle has been observed as being one of the most effective cycles for CO2, but sources have also indicated that for bottoming cycles, that is where the sCO2 cycle is used to generate electricity from waste heat, other cycle configurations should also be considered. In FlowNEX, the typical network diagram will look like the one on your right, where each component is interlinked to its neighboring element as to indicate the fluid flow. Each major component is modeled accordingly as to ensure that the correct pressure drop and heat transfer phenomena occurs. Over here we have the turbine, and where the turbine can be modeled using various correlations, such as the restrictor with loss coefficient or the ellipse law, or the component can contain a turbine performance chart. The compressor can also be modeled using a compressor chart over here. The recuperator can be modeled by using a simple heat transfer or via a more complex heat transfer correlation such as the Dietz-Boulter or Nielinsky correlation for convective heat transfer. Ambient conditions can also be modeled for the pipe element to simulate the effects of having an insulated versus a non-insulated pipe. The heat source and cooling can be modeled by integrating other cycles into the network, but more on this at the end of the webinar. Now, if we take a look at the design process, FlowNEX plays a critical role in each decision-making point. This includes cycle configuration evaluation, component size optimization, control during a plant trip, control for load ramp and efficiency, and balance of plant. In the initial process of the design phase, an appropriate cycle configuration evaluation must be done. This is to determine the optimal cycle configuration for a specific application, and since most applications are unique, it is vital to go through this process. Various cycle configurations exist, such as the simple recuperation cycle, the intercooling cycle, the reheating cycle, and the well-known recompression cycle, the preheating cycle, and many more. Therefore, having a tool to quickly run through various configurations and obtaining comparable results saves a lot of engineering time and money. In FlowNEX, this can be done primarily in two ways. The first way, using FlowNEX's user-friendly canvas. So without further ado, let's jump to FlowNEX. Here you can see I've created the simple recuperation cycle on the drawing canvas, where I've got a compressor, recuperator, turbine, heat source, cooling. I've also determined the efficiency by using FlowNEX's simple, user-friendly script, where the inputs and results have been defined, and my calculations have been done over here. This has been done for the intercooling cycle, the reheating cycle, the recompression cycle, the preheating cycle, and the turbine split flow. All the calculated efficiencies, I've added them to an Excel table, where I've created the bar graph to show the results. As you can see, the preheating and turbine split flow configurations should still be added. And just to show you how easy it is, I take the efficiency result, go to my Excel table, and drag and drop. And as you can see, the results update. Now for my turbine split flow, go to the efficiency, drag and drop the result, and the results update. Furthermore, I've created an input sheet where the hot temperature and the cold temperature of each cycle have been defined. Now I can change this parameter to say, for example, 450 degrees Celsius, where I would like to see the cycle's efficiencies at these different conditions. I solve, and in minimal time, I see the efficiencies update. This is extremely powerful to the engineer, as they can quickly see which is the best cycle configuration for their specific application. Now let's quickly jump back to our presentation. The next method is to use FlowNEX's API. In the event where the user wants to model hundreds of different configurations, varying the layout of components and not just the inputs, the API can be used to quickly construct different cycle configurations. The FlowNEX API uses the .NET framework, which enables the API to be used in almost any Windows application. This gives the user a lot of freedom to test hundreds of cycle configurations with minimal effort spent on building simulations, hereby preventing user errors and saving engineering time and money. In this case, the API can be used to start up and close FlowNEX, retrieve the results for all simulation entities, add new components or delete existing components, and link existing components. An example was created where we wanted to test 5 different configurations. This was done in a Python environment where the API was called and the different configurations were built using the API. The results were also recorded in an Excel table, and as you can see, here we can see the different configurations with their associated efficiency. We will now move on to component size optimization. Once the optimum cycle configuration has been determined for a specific application, the engineer now requires to calculate the optimum size of the different components in the cycle for optimum cycle efficiency. The biggest challenge in component sizing is how it will affect the cycle's overall efficiency. In the example below, we will look at how the length of a recuperator affects the net shaft power output. FlowNEX is able to model heat transfer and pressure drop. This gives us the ability to observe a realistic effect of changing the length of the recuperator on the cycle's net output power. The engineering principle is as follows. If the length is increased, more heat transfer occurs due to an increase in area, thus less heat is required to be added to our cycle, and this results in a more efficient cycle. However, a longer heat exchanger produces a higher pressure drop, and the compressor needs to work harder, taking power and reducing the efficiency of our cycle. An optimum point can therefore be achieved. By using FlowNEX's sensitivity analysis, we can vary our heat exchanger length and plot the resulting net power output of our shaft. Let's jump to FlowNEX. In this case, we're using the simple recuperating cycle, where we've got our compressor, turbine, heat source, cooling, and recuperator. In this case, we want to vary the length of our recuperator, so we created a parametric table with different cases, 10 in total, and different lengths. just make sure that the network solves, and as you can see in record time, it solves. Now we've plotted the heat exchanger length to the net power. The net power is calculated via the shaft, as you can see there. And if you go back to our chart over here, we can now basically just say run sensitivity analysis, and it will run through the different cases with different recuperator lengths. As you can see, the chart will start updating. And very quickly, we can already see that an optimum point is being reached. We will just wait for the simulation to finish. And there we go. As we can see from the chart, that the most net power that our cycle can deliver is at a point where the recuperation length is about 11.5 meters. Again, this is a very powerful feature that the engineer will find very useful in specifically determine various cycle parameters. If we jump back to our presentation, the next step in the design is we want to control the plant during a plant trip. In this case, we want to test a controller's ability to maintain a safe surge margin during a heat source trip. This can be done in FlowNEX, where the compressor operating point can be monitored in a compressor chart. In the example, we will simulate the trip of a heat source after 5 seconds. Due to the trip, the generator is then decoupled at 20 seconds, which results in the compressor and turbine speeding up, followed by a gradual decrease in speed, where the bypass valve opening is controlled using a PID controller. This is to ensure that the compressor does not go into surge. The advantage of being able to simulate a scenario like this is that the engineer can have a feel for the cycle, enabling the engineer to make better, more informative decisions regarding cycle and control design. Let us open FlowNEX and show how this was done. Again, we'll be using the same cycle where we've got our turbine inlet valve and also our bypass valve. What we will be doing is we will basically be simulating a heat source strip by lowering our temperature on here, on this boundary condition. We'll just solve, reload to steady state conditions, solve the network, and we will run the network. Actions has been set up beforehand as to simulate the scenario. As you can see, the heat source tripped. Going to our compressor chart, we can see that the compressor operating point is plotted here, and it will update as the simulation continues. Now we see after 20 seconds, the bypass valve will start acting. We'll just give it a moment as the simulation continues to solve, and as you can see, all the results are updating. Wait for the simulation to continue, and as you can see, the opening of the valve is being changed. Going back to the compressor chart, the speed of the compressor is slowing down, but luckily the compressor is not too close to the surge margin. And the simulation has stopped. Another interesting feature is that FlowNEX can be used to monitor critical temperature points in the cycle. This is to ensure that some points in the cycle don't go over a material limit temperature. For example, in this case, we used the recuperator inlet temperature, and in the first few seconds, the red line at the top over here, we can see due to the heat source strip, the temperature will lower. But then after 20 seconds, due to the bypass valve opening, and energy is no longer extracted by the turbine, we can see that the temperature will rise and peaks at a maximum of around 350 degrees Celsius. The bottom red line over here shows the opening of the valve. Jumping back to the presentation. Next, we will be looking at transient scenarios and how FlowNEX can be used to simulate and optimize control philosophies. FlowNEX includes a control library with the capability to model a complete DCS system alongside the thermal fluid system. This allows the engineer to evaluate detailed control systems designs in a single software package. In this specific example, we will be looking at the recompression cycle as described in the beginning of the webinar, where we have our main turbine and compressor, bypass compressor, two recuperators, our cooling, and our heating source. The scenario that we will be looking at is a load change where we reduce the heat source. As the heat source drops, the turbine inlet temperature drops, and we want to keep the cycle as close to the design point as possible. To counteract the turbine inlet temperature drop, we make use of a common control strategy called inventory control, where the mass of the cycle is reduced in order to maintain a specific turbine inlet temperature. In our example, the inventory control tank is at a specified pressure of 9.5 MPa, where the cycle's minimum and maximum pressure is at 9 MPa and 25 MPa. Thus, the inlet valve to the tank is situated just after the main compressor, and the tank outlet valve is situated just after the last recuperator or the cooler inlet. Valves are situated at the inlet and outlet of the tank, which can be opened or closed to increase or decrease the cycle's turbine inlet temperature. Furthermore, to maintain a cycle high efficiency, a specific flow bypass ratio is required. This is done by controlling the bypass compressor speed by using FlowNEX's built-in PID controller in the control library. For a detailed control study, the transient effects of the system component must be included. FlowNEX components already includes this in the form of thermal inertia in many components such as the piping and heat exchangers. The heat lost to the atmosphere is in this case simulated by the insulated pipe. The simulation is used to evaluate the change in cycle performance during a load change. On a side note, FlowNEX is also able to integrate with Simulink, where control philosophies can directly interact with parameters in the FlowNEX simulation environment. This is the case if you have already built a control system in Simulink and you would like to couple this to your FlowNEX thermal fluid network. Let's jump to the FlowNEX network. As you can see here, we've got the cycle with our compressor and turbine connected by a shaft. We've got our heat source, recuperators, inventory tank, cooling, and bypass compressor. I'll just load the steady state conditions, solve the network, and what we've done is we've plotted the important parameters. This includes the cycle mass, the turbine inlet temperature, and the heat input. Actions have been set up to control various aspects of our simulation, such as reducing the heat source as to simulate a reduce in load. So we go back to our graph over here and we run. Now this line indicates, the gray line indicates our load change. The blue line indicates our turbine inlet temperature, and the green line indicates our cycle mass. Going back to our simulation, we can see the results change. As you can see, our set point heat input has been reached, and the cycle adjusts our mass flow as to obtain a specific turbine inlet temperature. Also, through FlowNEX's implicit solver, we are able to solve very large time steps, as you can see here, as large as 5 seconds. And also, FlowNEX contains an adaptive time step, where the solver by itself recognizes if it starts becoming not stable, and it will actually change your time steps accordingly. So this enables the user not to focus on the time step size, but if the simulation is stable, it will increase the time step, and if it becomes unstable, it will decrease the time step. Now, as you can see here, the simulation stopped, and we can see that the turbine inlet temperature dropped because of the heat source going down, but then increased steadily to our set point as the mass of our cycle reduced. Coming back to our presentation, next we'll be looking at the balance of plant. FlowNEX is able to model various subsystems coupled to our main cycle. This includes various heat sources such as nuclear, waste heat systems or gas and coal combustion, various cooling systems such as cooling water or cooling towers. Also, one can also model various auxiliary systems such as fire safety systems, secondary cooling systems, and lubrication systems. FlowNEX provides the perfect environment where these systems can be linked with the main cycle to find quick and profitable engineering solutions to difficult system-level problems. For example, in the previous recompression cycle, we modeled the cooling water flow, which in turn influenced the cooling of our main cycle. As you can see here, is that we add a pump and heat exchanger. As we change the temperature on this, we can directly see how it affects the entire cycle. So just to recap, the software capabilities and features of FlowNEX includes a comprehensive component library, powerful and intuitive user interface, well-defined two-phase CO2 fluid properties, detailed fluid dynamic models, which includes but are not limited to choking, real gas behavior, etc., incremental heat transfer with framework for custom correlations, full transient capabilities including implicitly stable flow solver, adaptive time step functionality, thermal and rotational inertia, analog and digital DCS, built-in design and analysis features allowing for automated parametric studies. We hope you find the webinar very useful in your endeavor in finding the optimum sCO2 cycle, and that FlowNEX will be your tool of choice when it comes to systems design. There will be a pop-up on your screen in a moment with a link to our contact page. If you are interested by what you've seen today and would like a more detailed presentation, please click the link and complete a very short form, and we will contact you to provide more information specifically relevant to your company.